All right, listeners, buckle up. We're about to take a deep dive into the fascinating world of homological algebra. And our guide for this adventure is the book, Homological Algebra, by S.I. Gelfand and U.I. Manin. Now, I know the title might sound a bit intimidating, like something you'd find at a dusty corner of the library, but trust me, this book is full of incredible insights and mind-bending concepts.
It's funny, homological algebra is often seen as this very abstract area of math. But it's really all about finding hidden connections, like a secret code that unlocks the relationships between different mathematical ideas.
A secret code.
Ah,
That's a cool way to think about it. So for someone like me, coming into this fresh, where does the book take us first? What's the starting point for this journey into homological algebra?
well, it starts with the basics, laying the groundwork with concepts like complexes, cohomology, and exact sequences. Now, these terms might sound a bit technical, but they're actually quite visual.
Visual, you mean like we can actually picture these things in our minds?
Absolutely. Think of it like a chain of objects connected by arrows, kind of like a flow chart. These chains can represent all sorts of things, from geometric shapes to algebraic equations. And homological algebra helps us understand how these objects are related to each other within that chain.
Oh, I see. So instead of just looking at each object on its own, we're studying the relationships between them.
Exactly. And those relationships can reveal some pretty amazing patterns and properties that we might miss if we just focused on the individual objects themselves.
Okay, I'm starting to get it. But I'm a visual learner, so I need an example, something concrete that I can really wrap my head around.
All right. Picture a simple triangle. It has three sides. Those are one-dimensional objects, right? And it also has three vertices. Those are zero-dimensional objects. Now, homological algebra can help us analyze how these different dimensions are connected to each other within that triangle.
So we're not just talking about the shape of the triangle, but how its parts are linked across different dimensions. That's a whole new way of looking at something as simple as a triangle.
You got it. And by studying those connections, we can unlock some pretty incredible properties of the triangle, properties that wouldn't be obvious just from looking at its shape.
Wow, that's amazing. I'm starting to see how this kind of thinking could apply to so many fields, not just math. Any system where you have interconnected parts, right?
Absolutely. From networks and data structures to social interactions and even the structure of the universe itself. This idea of analyzing relationships between objects is incredibly powerful.
Okay, on to the next part of our journey. Now, the book introduces something called syzygies. It mentions Hilbert's work with them, and to be honest, they sound a bit like something out of a mystery novel.
Mysterious is a good word for them. They take us a level deeper. Syzygies aren't just about relationships, they're about relationships between
Oh,
relationships.
my brain just did a flip. Relationships between relationships. Okay, I need a translator here. Can you break that down for me?
Imagine you're designing a bridge. You've got a set of equations describing the forces acting on each beam, right? Those are our initial relationships. Now, syzygies would describe how those forces have to balance out across the entire structure for the bridge to be stable.
So syzygies are like a second layer of equations. They define the relationships between those initial force relationships.
You got it. It's like a hidden blueprint of stability within the bridge's design. And this concept isn't limited to just bridges. Think about ecosystems, financial markets, the internet. You have layers of relationships everywhere. And CCGs help us understand how those layers interact to create a functioning system.
Okay, my mind is officially blown. Understanding syzygies is like seeing the underlying code of a complex system.
Exactly. CCGs give us a deeper level of insight into how things are connected and how those connections influence the behavior of a system as a whole.
All right, let's keep moving. Now, the book starts to delve into some pretty heavy stuff like derived categories and triangulated categories. And I have to admit, this is where I started to feel a bit lost.
I understand. It's like going from a basic toolbox to a high-tech lab. These advanced categories provide a more abstract and powerful framework for applying homological algebra to even more complex problems.
So if syzygies are the code, these categories are like the advanced programming languages we need to understand how that code works.
That's a fantastic analogy. We're taking those fundamental concepts we've talked about, complexes, relationships, syzygies, and using them to construct even more sophisticated mathematical structures.
Okay, before we get too far ahead of ourselves, can you give me a real-world example of how these advanced tools are actually used? What kind of problems can we solve with them?
Absolutely. The book highlights a few fascinating applications. One that really stands out is something called mixed Hodge structures, which are used to analyze the geometry of complex algebraic varieties.
Okay, I'm going to need you to break that down for me a bit. Complex algebraic varieties sounds pretty intense.
Think of it this way. You're trying to understand the shape of a multidimensional object. But instead of just looking at it visually, you're using abstract algebra to describe its structure.
So it's like using algebra as a language to understand shapes that we can't even visualize in our minds.
You got it. And mixed Hodge structures, built using these advanced categories, give us a way to break down those complex shapes into smaller, more understandable pieces.
Wow, that's pretty mind-blowing. So these advanced categories are like giving us a new set of lenses to examine complex mathematical objects, objects that would be impossible to study otherwise.
Exactly. And that's just one example. There are many more applications of derived and triangulated categories, leading to all sorts of incredible insights across different areas of math and even beyond.
I'm definitely intrigued. But we've covered a lot of ground here, from the basic building blocks to these really advanced concepts. So I have to ask, what does it all mean? Why should someone care about homological algebra? What's the big takeaway here?
Because it gives you a new way of seeing the world. It reveals hidden patterns and connections that might otherwise be invisible. It's like having a special pair of glasses that let you see the underlying structure of complex systems, systems that, at first glance, might seem chaotic or random.
Okay, that's a powerful image. So what are some specific benefits for someone diving into this field?
Well, for one, it can help you simplify complexity. By breaking down intricate problems into smaller, more manageable pieces, you can gain a much deeper understanding of how they work.
So it's like having a deconstruction tool for complex systems. We can use homological algebra to break them down into their core components and see how they all fit together.
Precisely. Secondly, it can help you make connections between seemingly unrelated fields. Homological algebra helps you see the underlying similarities between different areas of study, which can lead to new insights and discoveries you might never have imagined.
It's like a universal translator for different areas of mathematics and even science.
Exactly. And finally, and perhaps most importantly, it can help you make new discoveries. This toolkit can lead to unexpected insights and breakthroughs in your field. By applying the principles of homological algebra, you might find solutions to problems that previously seemed impossible.
Okay, I'm convinced. Homological algebra is definitely worth exploring. But I'm curious, the book goes on to mention applications in robotics and AI. That seems like a huge leap from these abstract mathematical concepts. How does that even work?
It all comes down to recognizing that those fields also deal with complex systems. Robots, for example, are made up of interconnected parts, and their movements can be described as paths through a space. AI algorithms process information in complex ways, and understanding the structure of that information flow can help us improve their efficiency.
So the principles we've been talking about, analyzing relationships, understanding connections, even the idea of syzygies that can be applied to these real-world technologies.
Absolutely, and that just highlights the potential of homological algebra. It's not just a theoretical exercise. It has real-world applications that are still being discovered.
Well, for our listeners out there, here's something to think about. How might you use this powerful tool to solve problems or make discoveries in your own field? The possibilities really do seem endless. And that's what's so exciting about diving into a new field like this. You never know where it might lead.
There's always more to explore. And the beauty of homological algebra is that it can be applied in so many different ways. So keep learning, keep experimenting, and see where this journey takes you. It's amazing how homological algebra can reveal hidden information, like a secret code within these mathematical structures, things we wouldn't normally be able to see.
It's like we're using X-ray vision, but for math. The book mentions how homological algebra can even help us calculate these things called Betty numbers. Can you remind me what those are again?
Oh, sure. Betty numbers, they're a way to measure the number of holes in a space. Let's say you have a sphere, it's solid, no holes, right? So all its Betty numbers would be 0, except for the 0th one representing the sphere itself, and the 3rd one representing its interior. Now, if you take a torus, like a donut, it has 1 hole, right? So its first Betty number would be 1.
Right, I remember that. So you're saying homological algebra gives us this system for figuring out those Betty numbers. Like, it helps us understand the topology of a space, not just by looking at it, but by, like, analyzing its parts and how they're connected.
Exactly. We're going beyond just the shape. We're digging into the structure, the framework of the object. And the book mentions these things called chains that are part of this.
Chains. Oh, yeah, we talked about chains before, right? Like those flowcharts with the arrows connecting different things.
Right. But in this case, the chains, they actually represent the different dimensions of the space. So like with that triangle we talked about, there would be a chain representing the vertices, another for the edges, and so on.
And the Betty numbers, they're somehow encoded within these chains.
Precisely. We analyze how those chains relate to each other, how they're connected, and boom, we can figure out the Betty numbers. It's like we're using algebra to solve a geometry puzzle.
Whoa, that's so cool. And there's something about connecting homomorphisms, right? What do those do in all this?
Connecting homomorphisms are essential. Think of them like bridges, linking different parts of a complex together. They help us see how everything fits.
So they're like the glue that holds the whole structure together.
That's a great way to put it. And by studying those connections, those bridges between different levels of information, we get a much deeper understanding of the entire complex.
Okay, so we've got chains, we've got connecting homomorphisms, and Betty numbers. I think I'm starting to get the hang of this. But then the book throws in terms like singular complexes, simplicial sets, H cohomology. It all felt a bit like being thrown into the deep end.
Haha, I get it. Those are definitely more advanced ideas. But basically, they're all about finding different ways to represent and analyze topological spaces, but in a more abstract and general way.
So like we're building more advanced tools to deal with more complex spaces. And these tools, they have uses outside of just pure math, right?
Oh, absolutely. They're used in areas like algebraic topology, algebraic geometry. For instance, the book talks about the DRAM complex, which is this powerful tool for studying smooth manifolds.
The smooth manifolds, so like surfaces, curves, that kind of thing. But what exactly is the DRAM complex?
It basically uses differential forms to get information about the topology. Remember those from calculus? They're like a way to generalize derivatives and integrals to higher dimensions.
Oh yeah, right, right. So how do these differential forms help us understand the topology of, like, a curve or a surface?
Well, the DRAM complex, it assigns a specific set of these forms to each manifold. And by looking at the properties of these forms, we can learn about the topology of that manifold.
So we're using calculus to uncover the secrets of geometry. That's neat. And then there's something called Lie algebra cohomology. Lie algebras sound kind of intimidating.
They do have a dramatic name, right? But they're actually super important in mathematics. Lie algebras are used to study symmetry.
Symmetry.
Mhm.
How does that connect to homological algebra?
Well, Lie algebras have the special structure that works perfectly with homological methods, and by studying their cohomology, we can learn a lot about their structure and what are called their representations.
Representations, what does that mean?
Think of representations as ways of seeing a Lie algebra using things like matrices or linear transformations. It's a way to see how they actually act on other mathematical objects.
Oh, so it's like understanding how a Lie algebra influences its surroundings.
Exactly. And Lie algebra cohomology, it gives us a powerful way to understand these influences. And this is just the beginning. The book dives into even more complex topics like cyclic homology and spectral sequences.
Homology spectral sequences, they sound pretty intense.
They are advanced, for sure. But in simple terms, cyclic homology, it lets us study the algebraic properties of rings. And spectral sequences, well, they're kind of like a divide and conquer strategy.
Divide and conquer. In what way?
Well, they help us break down a huge, complex problem into a bunch of smaller, more manageable problems that we can solve step by step. And they have all sorts of applications, from algebraic topology to algebraic geometry.
Wow. We've gone from triangles to smooth manifolds to Lie algebras to spectral sequences. My head is spinning, but in a good way. It's incredible how broad this field of homological algebra is.
It really is a remarkable field. So many connections, so many uses. Don't worry if it takes time to grasp it all. The important thing is to appreciate the power and versatility of homological algebra.
It's really striking how homological algebra keeps bringing together these different parts of mathematics, like it's some kind of universal language they all speak.
That's a great point. We've seen how it ties in topology, algebra, geometry, even calculus. It gives us this framework to make sense of and solve problems across all these different areas.
It's really impressive how something so abstract can be so useful in so many areas. It makes me wonder, how did anyone even come up with this stuff? Like, where did homological algebra even begin?
That's a really interesting question. The answer actually lies in the history of math itself. Homological algebra, it really has its roots in the study of topology, particularly the work of mathematicians like Henri Poincaré and Emmy Noether back in the early 1900s.
Poincaré and Noether, those are some huge names in mathematics.
True pioneers. Poincaré, he was fascinated by the properties of shapes and spaces, and he developed these tools that laid the groundwork for algebraic topology. And Noethers, she was this brilliant algebraist who saw how you could use algebraic methods to understand topology. Her work with rings and modules, it turned out to be super important for homological algebra.
So is this collaboration between these giants of mathematics that sparked this whole new field.
Exactly. And their work inspired so many other mathematicians to build upon and refine the tools of homological algebra.
It's amazing how these early ideas have had such a huge impact, not just in math, but in other fields too.
You know, what often surprises people is that homological algebra isn't just for mathematicians working on super theoretical problems. It has real-world applications too.
That's what I always love to hear about. We touched on robotics and AI, but what are some other examples?
Well, one area where it's becoming more and more important is data analysis.
Data analysis. That's not what I would have expected. How does homological algebra fit into that?
Well, think about data. It often has this complex structure with all these relationships and connections between different data points. Homological algebra gives us the tools to analyze those relationships and pull out meaningful insights.
So instead of just crunching numbers, we can use homological algebra to, see the shape of the data.
Exactly, and that can help us understand patterns, trends, maybe even things that don't quite fit. Like imagine you're looking at a social network. You can use homological algebra to find clusters of users who have similar interests or connections.
So it's like a math way of finding those clicks everyone talks about.
Exactly. And that info, it can be super useful for things like advertising or understanding how information spreads through a network.
Wow, that's fascinating. Are there any other real-world uses?
Another area where homological algebra is showing a lot of promise is in image processing.
Image processing. Okay, now I'm really curious. How does that work?
So just like data, images have this complex structure, topologically speaking. Homological algebra can be used to identify features, detect edges, even rebuild images from incomplete data.
So it's like using abstract algebra to help us, see the world in a different way.
That's a great way to put it. And this has all sorts of applications: medical imaging, computer vision, even security.
It's incredible how something developed for such abstract math concepts can be so useful in the real world. Homological algebra is definitely a field to keep an eye on.
Absolutely. As more and more researchers realize how powerful it is, we can expect to see even more applications popping up in the future.
Well, I think that brings us to the end of our deep dive into homological algebra by Gelfand and Manon. This has been an incredible journey.
It has been quite a journey exploring all these complex ideas and connections.
I'm walking away from this deep dive with a whole new appreciation for the beauty and power of homological algebra. It's just remarkable how it ties together all these different parts of mathematics and even finds its way into real-world applications.
It really shows the power of thinking abstractly and how everything is connected in some way.
To our listeners, if you're feeling that spark of curiosity, I'd highly recommend checking out Gelfand and Manon's book. It's a challenge, for sure, but the rewards are definitely worth it.
And remember, homological algebra isn't just for mathematicians. It has the potential to make a difference in any field where you find complex relationships and structures.
So embrace the power of abstract thinking, dive into those hidden connections, and see where this amazing tool can take you. Until next time, happy diving.